we looked at depth pressure, and depth pressure doesn't seem to be too complicated, but I want to work through an example of this. Now I can do examples with submarines. That's completely fine, but I want to do something a little different. Let's say we have water and you are under the surface of the water. How many different old movies have you seen where someone takes a straw, like a reed straw, and hides under the surface of the water and is able to breathe through that? We're going to see what that looks like up to what depth we can manage. When you want to breathe in, your diaphragm contracts, it moves downwards. Your rib muscles, they expand your chest cavity. So the space around your lungs gets bigger. That makes the pressure inside your lungs drop just a little bit, and so air can move in. That means that in order to breathe, your chest has to be able to expand, at least a little bit. Your chest muscles and your diaphragm, they can generate a little bit of pressure difference. They can usually do a couple of kilopascals during regular breathing, and with a ton of exertion, you might be able to get a pressure difference of up to 10 kilopascals if you're in pretty good shape. Now, usually when we're under the water, we don't really care about this because you're not really trying to breathe underwater. But with a snorkel or a reed pipe or something that you are trying to breathe through, you are still trying to grab that air from the surface and breathe. The problem is your chest is fighting against this extra water pressure to be able to try to expand to make that space. So even though there is air available, if you can't expand your chest cavity to be able to pull that air in, none of it does you any good. So we're going to see how much water can be above you before that pressure differential becomes too much. Now, the density of water is 1,000 kilograms per cubic meter. And you might be thinking already, like, that's a big number to start with. This could be rough. It is. Pressure from depth is rho times g times d. We can get to 10 kilopascals is 10,000 pascals. That is our limit, and that's being pretty generous. So our pressure, we get our density of water, that's our 1,000 kilograms per cubic meter. We get gravity, 10 meters per second squared, times d equals our 10,000 pascal limit. Here's the problem. 1,000 times 10, that's 10,000. That is already most of the way there. This is really pascals per meter if you're keeping track of the units. Our distance that we can manage this is 1 meter. 1 meter below the surface, we are at a depth where there is enough water pressure above us to where even with maximum effort, we would not be able to breathe through a snorkel or anything like that. If you've ever wondered why snorkels have to be so short, why not just make the snorkel longer and then you can be farther under the surface? We just can't. Your chest doesn't do it. That's what scuba regulators are for. A scuba regulator just takes the tank of air and makes it at the same relative pressure as up at the surface, which means your chest is able to handle that just fine. So a different question. Let's say you've got the breathing thing figured out. You still have the problem of your eardrums. Your eardrums can withstand pressures. I mean, it will be painful pretty quickly, but your eardrums will rupture at about 35 kilopascals. So even if you're able to hold your breath, let's see how far down that is. 35 kilopascals is 35,000 pascals. Well, here's 10,000. Now we get D equals 3.5 meters. If we go much farther down than that, then we start to have real problems, and we start to get ruptured eardrums. Luckily, there is a safety mechanism. Your eardrums are connected to tubes that go from your middle ear to the back of your throat that help equalize pressure. And that's why when you yawn or swallow or chew gum or whatever, those tubes open and they let some air out. That's why your ears pop with altitude changes. If this doesn't happen, at least from time to time, while you are changing your altitude or your depth, then that pressure buildup starts to really accrue fast. If you are descending slowly and your ears are able to pop a couple times maybe, then you can keep that 35,000 Pascal pressure differential is a relative pressure. So as that pressure starts to build, if you can pop, you might decrease that relative pressure. And then you build again and pop, which is a whole lot better than if it's a sudden descent too quick to be able to pop, then you get there fast, and that's a problem.